A switched-mode power supply is an electronic power supply that incorporates a switching regulator to convert electrical power efficiently. Like other power supplies, an SMPS transfers power from a source, like mains power, to a load, such as a personal computer, while converting voltage and current characteristics. Unlike a linear power supply, the pass transistor of a switching mode supply continually switches between low dissipation, full on and full off states, and spends very little time in the high dissipation transitions, which minimizes wasted energy. Ideally, a switched mode power supply dissipates no power. Voltage regulation is achieved by varying the ratio of on to off time. In contrast, a linear power supply regulates the output voltage by continually dissipating power in the pass transistor. This higher power conversion efficiency is an important advantage of a switched-mode power supply. Switched-mode power supplies may also be substantially smaller and lighter than a linear supply due to the smaller transformer size and weight. Switching regulators are used as replacements for linear regulators when higher efficiency, smaller size or lighter weight are required. They are, however, more complicated. Their switching currents can cause electrical noise problems if not carefully suppressed, and simple designs may have a poor power factor. History: 1910, an inductive discharge ignition system invented by Charles F. Kettering and his company goes into production for Cadillac. This is a mechanically switched version of a flyback boost converter with an auto-transformer. Variations of this ignition system are in all non-diesel internal combustion engines. 1926, electrical condensers by Corsi mentions high-frequency welding and furnaces. Car 1936, car radios used electromechanical vibrators to transform the 6V battery supply to a suitable B+ voltage for the vacuum tubes. 1959, transistor oscillation and rectifying converter power supply system U.S. patent 3,040,271 is filed. 1970, high-efficiency power supply produced from about 1970 to 1995. 1972, HP 35, Hewlett-Packard's first pocket calculator, is introduced with transistor switching power supply for light-emitting diodes, clocks, timing, ROM, and registers. 1976, switched-mode power supply U.S. patent 4,097,773 is filed. 1977, Apple II is designed with a switching-mode power supply. For its time it was a breakthrough, since until then switching-mode power supplies were an unregistered trademark T used. Designed by Rod Holt. Rod Holt was brought in as product engineer and there were several flaws in Apple II that were never publicized. One thing Holt has to his credit is that he created the switching power supply that allowed us to do a very lightweight computer. 1980, the HP 8662A 10 kHz a Euro 1.28 GHz synthesized signal generator went with a switched power supply. Explanation: a linear regulator provides the desired output voltage by dissipating excess power and ohmic losses. A linear regulator regulates either output voltage or current by dissipating the excess electric power in the form of heat, and hence its maximum power efficiency is voltage out voltage and since the volt difference is wasted. In contrast, a switched-mode power supply regulates either output voltage or current by switching ideal storage elements, like inductors and capacitors, into and out of different electrical configurations. Ideal switching elements have no resistance when closed, and carry no current when open, and so the converters can theoretically operate with 100% efficiency. For example, if a DC source, an inductor, a switch, and the corresponding electrical ground are placed in series and the switch is driven by a square wave, the peak-to-peak voltage of the waveform measured across the switch can exceed the input voltage from the DC source. This is because the inductor responds to changes in current by inducing its own voltage to counter the change in current, and this voltage adds to the source voltage while the switch is open. If a diode and capacitor combination is placed in parallel to the switch, the peak voltage can be stored in the capacitor, and the capacitor can be used as a DC source with an output voltage greater than the DC voltage driving this circuit. This boost converter acts like a step-up transformer for DC signals. The buck-boost converter works in a similar manner, but yields an output voltage which is opposite in polarity to the input voltage. Other buck circuits exist to boost the average output current with a reduction of voltage. In an SMPS, the output current flow depends on the input power signal, the storage elements and circuit topologies used, and also on the pattern used to drive the switching elements. The spectral density of these switching waveforms is energy concentrated at relatively high frequencies. As such, switching transients and ripple introduced onto the output waveforms can be filtered with small LC filter. Advantages and disadvantages. The main advantage of the switching power supply is greater efficiency because the switching transistor dissipates little power when acting as a switch. Other advantages include smaller size and lighter weight from the elimination of heavy line frequency transformers, and lower heat generation due to higher efficiency. Disadvantages include greater complexity, the generation of high amplitude, high frequency energy that the low-pass filter must block to avoid electromagnetic interference, a ripple voltage at the switching frequency and the harmonic frequencies thereof. Very low-cost SMPSs may couple electrical switching noise back onto the mains power line, causing interference with AV equipment connected to the same phase. Non-power factor corrected SMPSs also cause harmonic distortion. SMPS and linear power supply comparison. There are two main types of regulated power supplies available, SMPS and linear. The following table compares linear regulated and unregulated AC to DC supplies with switching regulators in general. Theory of operation. Input rectifier stage. If the SMPS is an AC input, then the first stage is to convert the input to DC. This is called rectification. A SMPS with a DC input does not require this stage. In some power supplies, the rectifier circuit can be configured as a voltage doubler by the addition of a switch operated either manually or automatically. This feature permits operation from power sources that are normally at 115 V or at 230 V. The rectifier produces an unregulated DC voltage which is then sent to a large filter capacitor. The current drawn from the main supply by this rectifier circuit occurs in short pulses around the AC voltage peaks. These pulses have significant high-frequency energy which reduces the power factor. To correct for this, many newer SMPS will use a special PFC circuit to make the input current follow the sinusoidal shape of the AC input voltage, correcting the power factor. Power supplies that use active PFC usually are auto-ranging, supporting input voltages from 100 VAC 250 VAC, with no input voltage selector switch. A SMPS designed for AC input can usually be run from a DC supply, because the DC would pass through the rectifier unchanged. If the power supply is designed for 115 VAC and has no voltage selector switch, the required DC voltage would be 163 VDC. This type of use may be harmful to the rectifier stage, however, as it will only use half of diodes in the rectifier for the full load. This could possibly result in overheating of these components, causing them to fail prematurely. On the other hand, if the power supply has a voltage selector switch for 115 230 V, the selector switch would have to be put in the 230 V position, and the required voltage would be 325 VDC. The diodes in this type of power supply will handle the DC current just fine because they are rated to handle double the nominal input current when operated in the 115 V mode, due to the operation of the voltage doubler. This is because the doubler, when in operation, uses only half of the bridge rectifier and runs twice as much current through it. It is uncertain how an auto-ranging active PFC-type power supply would react to being powered by DC. Inverter stage. This section refers to the block marked chopper in the diagram. The inverter stage converts DC, whether directly from the input or from the rectifier stage described above, to AC by running it through a power oscillator, whose output transformer is very small with few windings at a frequency of tens or hundreds of kilohertz. The frequency is usually chosen to be above 20 kHz, to make it inaudible to humans. The switching is implemented as a multistage MOSFET amplifier. MOSFETs are a type of transistor with a low on resistance and a high current handling capacity. Voltage converter and output rectifier. If the output is required to be isolated from the input, as is usually the case in mains power supplies, the inverted AC is used to drive the primary winding of a high-frequency transformer. This converts the voltage up or down to the required output level on its secondary winding. The output transformer in the block diagram serves this purpose. If a DC output is required, the AC output from the transformer is rectified. For output voltages above 10 volts or so, ordinary silicon diodes are commonly used. For lower voltages, Schottky diodes are commonly used as the rectifier elements. They have the advantages of faster recovery times than silicon diodes and a lower voltage drop when conducting. For even lower output voltages, MOSFETs may be used as synchronous rectifiers. Compared to Schottky diodes, these have even lower conducting state voltage drops. The rectified output is then smoothed by a filter consisting of inductors and capacitors. For higher switching frequencies, components with lower capacitance and inductance are needed. Simpler, non-isolated power supplies contain an inductor instead of a transformer. This type includes boost converters, buck converters, and the buck-boost converters. These belong to the simplest class of single-input, single-output converters which use one inductor and one active switch. The buck converter reduces the input voltage in direct proportion to the ratio of conductive time to the total switching period, called the duty cycle. For example, an ideal buck converter with a 10 V input operating at a 50% duty cycle will produce an average output voltage of 5 V. A feedback control loop is employed to regulate the output voltage by varying the duty cycle to compensate for variations in input voltage. The output voltage of a boost converter is always greater than the input voltage, and the buck-boost output voltage is inverted but can be greater than, equal to, or less than the magnitude of its input voltage. There are many variations and extensions to this class of converters, but these three form the basis of almost all isolated and non-isolated DC-to-DC converters. By adding a second inductor, the AUC and SEPIC converters can be implemented, or, by adding additional active switches, various bridge converters can be realized. Other types of SMPSs use a capacitor diode voltage multiplier instead of inductors and transformers. These are mostly used for generating high voltages at low currents. The low-voltage variant is called charge pump. Regulation. A feedback circuit monitors the output voltage and compares it with a reference voltage, which shown in the block diagram serves this purpose. Depending on design safety requirements, the controller may contain an isolation mechanism to isolate it from the DC output. Switching supplies in computers, TVs and VCRs have these optocouplers to tightly control the output voltage. Open-loop regulators do not have a feedback circuit. Instead, they rely on feeding a constant voltage to the input of the transformer or inductor, and assume that the output will be correct. Regulated designs compensate for the impedance of the transformer or coil. Monopolar designs also compensate for the magnetic hysteresis of the core. The feedback circuit needs power to run before it can generate power, so an additional non-switching power supply for standby is added. Transformer design. Any switched-mode power supply that gets its power from an AC power line requires a transformer for galvanic isolation. Some DC-to-DC converters may also include a transformer, although isolation may not be critical in these cases. SMPS transformers run at high frequency. Most of the cost savings in offline power supplies result from the smaller size of high-frequency transformer compared to the 50/60 Hz transformers formerly used. There are additional design trade-offs. The terminal voltage of a transformer is proportional to the product of the core area, magnetic flux, and frequency. By using a much higher frequency, the core area can be greatly reduced. However, core losses increase at higher frequencies. Cores generally use ferrite material which has a low loss at the high frequencies and high flux densities used. The laminated iron cores of lower frequency transformers would be unacceptably lossy at switching frequencies of a few kilohertz. Also, more energy is lost during transitions of the switching semiconductor at higher frequencies. Furthermore, more attention to the physical layout of the circuit board is required as parasitics become more significant, and the amount of electromagnetic interference will be more pronounced. Copper loss. At low frequencies, designers can usually ignore the skin effect. For these frequencies, the skin effect is only significant when the conductors are large, more than 0.3 inches in diameter. Switching power supplies must pay more attention to the skin effect because it is a source of power loss. At 500 kHz, the skin depth in copper is about 0.003 inches, a dimension smaller than the typical wires used in a power supply. The effective resistance of conductors increases, because current concentrates near the surface of the conductor and the inner portion carries less current than at low frequencies. The skin effect is exacerbated by the harmonics present in the high-speed PWM switching waveforms. The appropriate skin depth is not just the depth at the fundamental, but also the skin depths at the harmonics. In addition to the skin effect, there is also a proximity effect, which is another source of power loss. Power factor. Simple offline switched-mode power supplies incorporate a simple full-wave rectifier connected to a large energy-storing capacitor. Such SMPSs draw current from the AC line in short pulses when the mains instantaneous voltage exceeds the voltage across this capacitor. During the remaining portion of the AC cycle, the capacitor provides energy to the power supply. As a result, the input current of such basic switched-mode power supplies is high harmonic content and relatively low power factor. This creates extra load on utility lines, increases heating of building wiring, the utility transformers, and standard AC electric motors, and may cause stability problems in some applications such as in emergency generator systems or aircraft generators. Harmonics can be removed by filtering, but the filters are expensive. Unlike displacement power factor created by linear inductive or capacitive loads, this distortion cannot be corrected by addition of a single linear component. Additional circuits are required to counteract the effect of the brief current pulses. Putting a current-regulated boost chopper stage after the offline rectifier can correct the power factor, but increases the complexity and cost. In 2001, the European Union put into effect the standard IEC EN 61000-3-2 to set limits on the harmonics of the AC input current up to the 40th harmonic for equipment above 75 AW. The standard defines 4 classes of equipment depending on its type and current waveform. The most rigorous limits are established for personal computers, computer monitors, and TV receivers. To comply with these requirements, modern switched-mode power supplies normally include an additional power factor correction stage. Types: switched-mode power supplies can be classified according to the circuit topology. The most important distinction is between isolated converters and non-isolated ones. Non-isolated topologies, non-isolated converters are simplest, with the 3 basic types using a single inductor for energy storage. In the voltage relation column, D is the duty cycle of the converter, and can vary from 0 to 1. The input voltage is assumed to be greater than 0. If it is negative, for consistency, negate the output voltage. When equipment is human accessible, voltage and power limits of less than or equal to 42.4 V peak/60 VDC and 250 VA apply for safety certification. The buck, boost, and buck-boost topologies are all strongly related. Input, output and ground come together at one point. One of the 3 passes through an inductor on the way, while the other 2 pass through switches. One of the 2 switches must be active, while the other can be a diode. Sometimes, the topology can be changed simply by relabeling the connections. A 12V input, 5V output buck converter can be converted to a 7V input, a 5V output buck boost by grounding the output and taking the output from the ground pin. Likewise, SEPIC and Zeta converters are both minor rearrangements of the A converter. The neutral point clamp topology is used in power supplies and active filters and is mentioned here for completeness. Switches become less efficient as duty cycles become extremely short. For large voltage changes, a transformer topology may be better. Isolated topologies. All isolated topologies include a transformer, and thus can produce an output of higher or lower voltage than the input by adjusting the turns ratio. For some topologies, multiple windings can be placed on the transformer to produce multiple output voltages. Some converters use the transformer for energy storage, while others use a separate inductor. One flyback converter logarithmic control loop behavior might be harder to control than other types. 2. The Ford converter has several variants, varying in how the transformer is reset to zero magnetic flux every cycle. Quasi-resonant zero-current zero-voltage switch. In a quasi-resonant zero-current zero-voltage switch, each switch cycle delivers a quantized packet of energy to the converter output, and switch turn-on and turn-off occurs at zero current and voltage, resulting in an essentially lossless switch. Quasi-resonant switching, also known as valley switching, reduces ME in the power supply by two methods: by switching the bipolar switch when the voltage is at a minimum to minimize the hard switching effect that causes ME. By switching when a valley is detected, rather than at a fixed frequency, introduces a natural frequency jitter that spreads the RF emissions spectrum and reduces overall ME. Efficiency and ME, higher input voltage in synchronous rectification mode makes the conversion process more efficient. The power consumption of the controller also has to be taken into account. Higher switching frequency allows component sizes to be shrunk, but can produce more RFI. A resonant Ford converter produces the lowest ME of any SMPS approach because it uses a soft switching resonant waveform compared with conventional hard switching. Failure modes. For failure in switching components, circuit board and so on, read the failure modes of electronics article. Power supplies which use capacitors suffering from the capacitor plague may experience premature failure when the capacitance drops to 4% of the original value. This usually causes the switching semiconductor to fail in a conductive way. That may expose connected loads to the full input volt and current, and precipitate wild oscillations in output. Failure of the switching transistor is common. Due to the large switching voltages this transistor must handle, these transistors often short out, in turn immediately blowing the main internal power fuse. Precautions. The main filter capacitor will often store up to 325 volt long after the power cord has been removed from the wall. Not all power supplies contain a small bleeder resistor to slowly discharge this capacitor. Any contact with this capacitor may result in a severe electrical shock. The primary and secondary side may be connected with a capacitor to reduce ME and compensate for various capacitive couplings in the converter circuit, where the transformer is one. This may result in electric shock in some cases. The current flowing from line or neutral through a 2000I copyright resistor to any accessible part must, according to IEC 60950, be less than 250 1/4 A for IT equipment. Applications. Switched mode power supply units in domestic products such as personal computers often have universal inputs, meaning that they can accept power from mains supplies throughout the world, although a manual voltage range switch may be required. Switch mode power supplies can tolerate a wide range of power frequencies and voltages. In 2006, at an Intel Developers Forum, Google engineers proposed the use of a single 12V supply inside PCs, due to the high efficiency of switch mode supplies directly on the PCB. Due to their high volumes, mobile phone chargers have always been particularly cost-sensitive. The first chargers were linear power supplies, but they quickly moved to the cost-effective ringing choke converter SMPS topology, when new levels of efficiency were required. Recently, the demand for even lower no-load power requirements in the application has meant that flyback topology is being used more widely. Primary side sensing flyback controllers are also helping to cut the bill of materials by removing secondary side sensing components such as autocouplers. Switched mode power supplies are used for DC to DC conversion as well. In automobiles where heavy vehicles use a nominal 24V DC cranking supply, 12 volts for accessories may be furnished through a DC-DC switch mode supply. This has the advantage over tapping the battery at the 12-volt position that all the 12-volt load is evenly divided over all cells of the 24-volt battery. In industrial settings such as telecommunications racks, bulk power may be distributed at a low DC voltage and individual equipment items will have DC-DC switched mode converters to supply whatever voltages are needed. Terminology: the term switch mode was widely used until Motorola claimed ownership of the trademark switch mode, for products aimed at the switching mode power supply market, and started to enforce their trademark. Switching mode power supply, switching power supply, and switching regulator refer to this type of power supply. See also: autotransformer, boost converter, conducted electromagnetic interference, DC to DC converter, inrush current, Joule thief, leakage inductance, switching amplifier, transformer, vibrator. Notes. References: Pressman, Abraham I., Switching Power Supply Design, McGraw-Hill, ISBN A0-07-052236-7. Further reading: Basso, Christoph, Switch Mode Power Supplies, SPI Simulations and Practical Designs, McGraw-Hill, ISBN A0-07-150858-9. Basso, Christoph, Designing Control Loops for Linear and Switching Power Supplies, a Tutorial Guide, Artec House, ISBN A978-16080755577. Brown, Marty, Power Supply Cookbook, Nunes, ISBN A0-7506-7329. Zhao, Ericsson, Robert W. Maximovich, Dragon, Fundamentals of Power Electronics, ISBN A0-7923-7270-0. Liu, Mingliang, Demystifying Switched Capacitor Circuits, Elsevier, ISBN A0-7506-7907-7. Luo, Fang Lin. Yi, Hong, Advanced DC-DC Converters, CRC Press, ISBN A0-8493-1956-0. Luo, Fang Lin. Yi, Hong. Rashid, Mohammed H., Power Digital Power Electronics and Applications, Elsevier, ISBN A0-12-088757-6. Maniktala, Sanjay, Switching Power Supply Design and Optimization, McGraw-Hill, ISBN A0-07-143483-6. Maniktala, Sanjay, Switching Power Supplies A to Z, Nunes. Elsevier, ISBN A0-7506-7970-0. Maniktala, Sanjay, Troubleshooting Switching Power Converters, A Hands-On Guide, Nunes. Elsevier, ISBN A0-7506-8421-6. Moen. Ned. Undland, Tor M. Robbins, William P., Power Electronics are Converters, Applications, and Design, Wiley, ISBN A0-471-22693-9. Nelson, Carl, LT 1070 Design Manual AN19, Linear Technology Application Note giving an extensive introduction in buck, boost, CUK, inverter applications. Pressman, Abraham I. Billings, Keith. Morey, Taylor, Switching Power Supply Design, McGraw-Hill, ISBN A0-07-148272-5. Rashid, Mohammed H., Power Electronics, Circuits, Devices, and Applications, Prentice Hall, ISBN A0-13-122815-3. External links, media related to switched mode power supplies at Wikimedia Commons, Load Power Sources for Peak Efficiency, by James Colotti, published in EDN October 5, 1979, Globtech, Incorporated. Glossary of switched mode power supply terms.